In this lesson, we'll be reviewing event simulation results. After completing this lesson, you'll be able to review simulation results. Now that the simulation solve has finished, let's take a look at the results. I do want to make a note that simulation solves for event simulation can take a considerable amount of time. Based on the complexity and the dynamics of your model, you might see a timeout error after 12 hours of solve. So this is why it's important to understand the mesh element size, the resolution, the duration of the event, and the number of steps and how they affect the model. Make sure that if you're not looking for self-intersections, or if you can solve any of the bodies as rigid bodies and omit them from the simulation, this will really help speed up the calculation time. And often if you notice that a simulation is hung for a while, go ahead and cancel the simulation solve, make some adjustments, maybe change some parameters, and then resolve the study. Oftentimes you might find that based on the amount of traffic on the server that you might see a simulation hang. So it's a good idea just to keep an eye on that. If it's going to get past the 12-hour mark, that likely means that your model is too complex or the interactions are too complex, and you might want to revisit your contact sets, the materials, or maybe the mesh resolution. But for our results here, we have several different things that we can look at. Just like with static stress and nonlinear studies, we can look at things like stress, displacement, strain, and reaction force, but note that there's no safety factor here. We also have acceleration and velocity. We're going to start by taking a look at stress, and specifically the von Mises stress. I'm going to use my display option to toggle the mesh to give me a good idea of the mesh elements and how the information breaks down. Do note also that we do have some options. We can go into our legend options and we can change the color transition to be banded, which will show each mesh element as a single color, and it'll give us a better idea of the stresses involved in those areas. I like to use the smooth transitions in most cases, but there are times when changing that color transition can be helpful. So when we're looking at results for an event simulation, we have a slider that is representative of the number of steps we set up in our study. We can use the slider to navigate through the event, and we can see how the bodies are reacting to the forces. In this case, if we go all the way to step 13, we rotate this around, we can see that we have an area of high stress at the bottom of the plate, which is what we would expect to see. But also note that along the seams of some mesh elements, especially over here and over here, we see some stress risers or some areas of high stress concentration. Now typically we see those here because of the bonded contact set between the plate and the blocks. This might be a good way for you to identify any potential design errors in, for example, a forming tool. You might want to revisit how you hold the plate to make sure that you're not increasing the stress in certain areas. This could be an example of maybe rounding the corner here so that you don't have a sharp corner that we're pulling against, or it could be many other things. So as we're looking at this model and we're going through each step in the process, we also have a 2D chart, and the chart will help us identify the specific step as well as the value. So we can traverse through this by moving the bar left and right. We can zoom in and we can zoom out. And we can get a good idea of what we're seeing in terms of the actual values. We can also use the inspect tools such as point or surface probes to identify the loading in certain areas. For example, right here, we're going to place a point probe right there, and as we traverse through the steps, we can see what that stress load is. We can also change the deformation. Right now what we're looking at is the actual deformation of the model. While we would typically expect to see deformations like this on a static stress study when it has an adjusted deformation, what we're seeing here is the true deformation of the sheet. So this is also something to keep in mind, that we're not looking at an adjusted model. Let's take a look at some of the other display options. For example, the displacement. Now we would expect to see the max displacement at the bottom position here. So there's nothing here that's sort of out of the ordinary. We can take a look at reaction forces, and while we're not analyzing the stress in the form tool itself, we are looking at the reaction forces And that's going to show us some reaction forces between the two. But note that the value, at least on our surface probe, is 0, but the max and min values are not really calculated here because we're not looking at the deformation of those tools. We also have strain, which we see a higher strain along that sharp edge, as well as isolated in the bottom where the forming tool has the interaction with the plate. And then again, we can look at acceleration and velocity, and we can see exactly how quickly things are changing. So we can see at this position, we have a maximum right along these edges. And this might tell us that we need to start our forming tool slower into the plate rather than hitting it with a certain velocity. So again, we're looking at a very simplified case here. We're looking specifically at some sort of mass being pushed down into a plate, and we wanted to see how it deformed. This isn't the only thing event simulation is good for. Again, we can take a look at a situation where the part is actually breaking and allow those mesh elements to pull apart. We can take a look at things like plastic parts, snap fit pieces, making sure that they can actually hold up to the loads as we insert them. We can also take a look at forming tools like this. We could get a little bit more involved and make sure that the forming tool isn't going to actually push the material past the point of yield and actually shear or break it. This is as far as we're going to take this example, but it is a great tool to play around with, especially since it is a preview technology and there's no cloud credit cost associated with solving these studies. It's a good idea to just play around with the setup, use some basic parts like this, a plate, some blocks, and an anvil, and just simply see how they deform and get a good idea of what this tool can do for you. From here, we do want to make sure that we have saved the file before we move on.